Hello, my name is Abby Sitterman, and I'm an undergraduate researcher with the Utah Neurorobotics Lab. I'm incredibly excited to share some of my research with you today. We'll be discussing electrocutaneous stimulation, which is a low-cost and non-invasive method of providing sensory feedback, and the fact that low frequencies improve intensity discrimination. Electrocutaneous stimulation uses electrodes on the skin to evoke tactile sensation, and as previous studies have concluded, stimulation of amputees and intact participants yield very similar results. So we place our stimulation pad on a residual limb or an intact palm, where the sensory nerve endings will receive the stimuli. Action potentials will propagate along the natural pathways through the spinal cord up to the brain where it is consciously perceived. We want to ensure that the magnitude of tactile stimulation is conveyed because that is an essential characteristic of natural touch. So here we are exploring the ability to discriminate between electrocutaneous stimulation frequencies. The way we set up our experiment was a two-alternative forced-choice paradigm in which participants were provided two stimuli and asked to tell us which was stronger. So the test stimulus, if much weaker than the reference stimulus, the probability of it being judged stronger would be 0. Whereas if it's much higher, the probability of it being judged stronger would be 1. And if the reference and test stimuli are equal, the probability of either being judged stronger would be 0.5. This translates to the plot we see here, which quantifies the just noticeable difference, or J&D, which is the minimum change in stimulation frequency that can be identified correctly 75% of the time. So you see that the percent judged stronger in between 0.25 and 0.75, those designate the just noticeable difference, the lower and upper, which then brings us to Weber's law, which is that the J&D is proportional to the absolute magnitude of the stimulus. This then translates into the Weber fraction, which is the percent change, which is consistent across stimulus magnitude. In other words, the greater the stimulus magnitude, the greater the change needed in order to be able to perceive it. Here we show that Weber's law does not hold true for at least electrocutaneous stimulation, where the Weber fraction is much smaller at lower frequencies. Weber fractions here are 4 standards fit to psychometric functions, where sharper curves indicate improved performance. The sharpest curve is corresponding to our 25 Hz standard, which is our smallest frequency standard. And this weakest or gentlest curve is corresponding with our 100 Hz standard, which is our highest frequency standard. So we can see that improved performance is significant, and there's far greater discriminability at these lower frequencies. Weber fractions are much smaller and show greater discriminability at lower frequencies. The first 4 here, corresponding with the electrocutaneous, the 4 standards we saw in the traces up above, and these are compared to intraneural and epineural with the Utah slanted electrode array and the cuff electrode, respectively, which are leading invasive methods of stimulation. These are more expensive, higher risk, and quite honestly, they're far less accessible. And so electrocutaneous is far more accessible, and the fact that our results are very comparable, if not improved. Comparing the navy blue, we have our electrocutaneous at a 25 Hz standard. Compared to the epineural, we're performing far better with much greater discriminability. And so we're going to be able to provide sensory feedback for those with upper limb prostheses. Application of that's just so exciting. Lower Weber fractions result in a higher number of perceivable sensory gradations, which indicates more natural and intuitive sensory feedback. This table here shows the Weber fractions increasing and the number of sensory gradations decreases. If you're to think of sensory gradations on-off, that would be 2 gradations, or soft, medium, hard would be 3. If Weber's law held true, there would only be 14 sensory gradations across this span of frequency. And that static Weber fraction would result in very large and discrete steps, whereas a dynamic Weber fraction, based on the data that we found here, shows that the steps in perceived intensity are much smoother. They're far more similar to what the perceived intensity curve would be for a natural hand. And so we're able to achieve far more natural and intuitive sensory feedback because Weber's law does not hold true, and we're able to have these variable fractions across the span of frequencies. Our future work includes circumventing supplementary sensory cues that might be helping in discrimination at these lower frequencies. At the lowest frequency, you can perceive individual pulses, and it's more of a tapping sensation. The spacing between each pulse is very noticeable, whereas at higher frequencies, perceivable constant pulse, and so that's more of a vibration. You can no longer feel spaces. So the spacing may be providing additional timing cues that's aiding in the discrimination, and we want to isolate frequency per set. The application of this is so incredible, and the potential to provide those with more natural and intuitive sensory feedback. If you have any questions, feel free to reach out to me. Thank you so much.